Welcome to the Structured Cabling lecture series. This is lesson number 8, Definitions of Electrical Parameters. In this lesson, I will go over the TIA-568.2-D Standard. The industry standards guide the installation, maintenance, and testing of products and technologies for a variety of security, industrial, and enterprise networks. The definition of electrical parameters are defined under the TIA, which is basically the Telecommunications Industry Association Standard 568.2-D. So that's why I will be covering these items under that particular standard, TIA 568.2-D Standard. Do you need to know these particular standard items for your exams? In most structured cabling environments, in most structured cabling exams and lectures that you take in the university, you will need to memorize or know this like back of your hand. Again, you need to understand what they are, but sometimes simple memorization, such as to know that TIA 568.2-D standard is covering this definition, may save you a few points on your structured cabling exams. So the first definition I will cover is the return loss. A return loss is a measure of the degree of impedance mismatch between two impedances. It is the ratio expressed in decibels of the amplitude of a reflected wave echo to the amplitude of the main wave at the junction of a transmission line and a terminating impedance. The factors affecting the return loss of typical Cat6 cabling include the cable quality and the frequency. Cable quality may be things like connectors and terminations. So poorly constructed cables with irregular twisting or inconsistent insulation can result in a greater impedance variations, leading to increased return loss. Improperly installed or substandard connectors can also could increase the impedance, and also loss or untwisted termination. Loose or untwisted termination are common issues with return loss as well. So if you have an untwisted termination point or a very loose termination, that could cause a lot of impedance. In terms of frequency, like cable length is another problem that will result in return loss. So return loss decreases, in other words, worsen at a higher frequencies as even small impedance mismatch become more significant, right? The longer cable can also amplify the effects of impedance mismatches. So you need to understand that for your exams when you are discussing return loss. So that's our first definition. The next definition is the insertion loss. This term has replaced the term attenuation. So maybe you heard from your parents or your colleagues or your friends the term attenuation. So signal attenuation is what we are looking at here. So it is a measure of the decrease of signal strength as it travels down the media. So in other words, media is basically like a wire, right? So insertion loss is basically we are looking at signal attenuation or signal degradation. You could look at that way as well. You need to understand also the factors affecting the insertion loss in a Cat6 cabling environment in most of your exams. So those includes cable length, frequency, cable quality, connectors and splicers, signal reflection, etc. So insertion loss can be caused by any of those items. In terms of cable length, for example, the longer the cable, the greater the insertion loss. You need to understand that always. Typically any time when we have some kind of a loss, greater the length of a cable, well, the greater the loss. That's going to be the running theme for this entire lecture. So Cat6 cables are also rated up to, remember, 100 meters, but insertion loss increase significantly beyond that length. So you could have a Cat6 cable that is longer than 100 meters. However, the insertion loss is going to be far greater, like almost at a logarithmic scale, increase. Frequency, insertion loss increases with higher frequencies. At a higher frequencies, more energy is absorbed by the cable material. So the copper wires absorb the energy. As a result of it going to create an insertion loss. Cable quality is another one. The poorly manufactured cables may have a higher resistance. Guess what higher resistance cause? Well, signal as attenuation, also poor insulation or inconsistent twist within that poor cable quality could cause a greater insertion loss. Another one that some instructors may forget is the temperature. Insertion loss is higher with the higher temperatures, as higher temperatures increases the resistance of the conductors, resulting in more signal loss. So if you're in a warm environment, hot environment, humid environment even, because humidity could potentially have an impact on the increased temperatures felt by the cable, that could cause a higher insertion loss. Again, even for insertion loss, connectors and splicers could also increase insertion loss. Each connector or splice adds a small amount of insertion loss, and so more connectors and splicers you have within a run, it's going to create a high insertion loss. Poorly installed terminations can also increase in insertion loss, and also signal reflection, which is an impedance mismatch between the cable and the connectors, can also lead to a greater signal loss or insertion loss. So those are the things you need to understand with insertion loss. The next one is basically next loss. Next loss, get it? So it's called the next loss, which is basically the near end crosstalk, also known as a next loss. It's a measure of the unwanted signal coupling from a transmitter at the near end into the neighboring non-energized pair measured at the near end. So what does that basically mean? It is primarily caused by a poorly twisted or split wire pairs and termination issues. Specifically, next occurs when signal from one wire pair are picked up by the adjacent pair, leading to a signal degradation. So if you have whole bunch of cables with this type of twisting, like minimal minimal untwist, it's going to be less next loss. But if you have a lot of if this is untwisted all the way up here, the next loss is going to be a little bit higher. So you need to be careful with termination of your cables, because that is one of the key things that could lead to the next loss. PS next loss is basically Powersum near end crosstalk. What is it? Basically is a computation of the unwanted signal coupling from multiple transmitters at the near end into a neighboring non-energized pair measured at the near end. So in other words, it is a summation of individual next effect, which we learned in the previous slide, on each pair by the other pairs. So it is like the next loss, but it is a summation of the individual next loss effect on each pair on by the other pair. So this is what we call a type of crosstalk that is caused by nearby cables. So this is like a next loss, but it is what we are looking at, the summarization of the entire next effect. Next one you should be familiar with for your exams is the FEXT loss, also known as the far end crosstalk. It's a measure of the unwanted signal coupling from a transmitter at the near end into the neighboring pair measured at the far end. Again, you need to know what causes the FEXT loss, also known as FEXT loss. So those are caused by poor cable insulation and cable quality, pretty much. So in this particular type of loss, a kink or a damaged cables, which is bends, kinks, or other cable damage, can alter the impedance and increase the FEXT or FEXT loss. Improper termination, which is incorrectly terminated connectors or connection points, can introduce impedance mismatches and increase FEXT. Excessive length. So if you have a longer cable, even within the specification, for example, Cat6 have 100 meters, even 100 meter Cat6 cable will tend to have a higher FEXT due to increased coupling between pairs compared to less having a shorter cable. Another key is the cable quality. Again, poorly twisted pairs, improper shielding both of these things could cause FEXT loss. If the twist in the pairs are not tight enough or the cable shielding is inadequate, signals can leak between pairs, leading to FEXT. Again, poor shielding can allow electromagnetic interference to affect signals and increase crosstalks. So improper shielding, poor twisted pairs, those are the two things that also can cause a lot of FEXT loss or FEXT loss, right? Environmental factors can impact this as well. So electromagnetic interference in this case, and also temperature, just like some other losses that we previously discussed. Electromagnetic interference is EMI, which is a nearby electrical equipment or other sources of EMI that can introduce noise into that cable, which interferes with the signal, which in return increase the FEXT loss. With extreme temperatures, on the other hand, also can have an effect on the cable impedance and contribute to FEXT loss. So you need to understand in depth how these things impact the FEXT loss, how it interact with this type of loss for your exams and labs. So the next one we're going to look at is the attenuation to crosstalk ratio find, and also known as the equal level far end crosstalk, also known as ACRF or ELF EXT loss. So it's a measure of the unwanted signal coupling from a transmitter at the near end into the neighboring pair measured at the find relative to the receive signal level measured on that same pair. Again, if you can't even understand what this definition is, at least memorize it for your exam. I'm telling you, because when you go to the field, you will eventually understand if you don't understand right now. I know it's a lot of words, but remember, it's a measure of the unwanted signal coupling from a transmitter at the near end into the neighboring pair measured at the find relative to the received signal level measured at the same pair. So that's the key thing you need to understand. So what causes ACRF or ELF EXT loss? Well, a poor ACRF levels can result in increased bitrate errors, or typically it's undeliverable signal packets. Note that the NEXT loss or next loss margin alone is not sufficient to ensure that the proper ACRF performance, right? So a critical consideration in determining the capability of a cabling system is the difference between insertion loss and the near end crosstalk EXT loss, right? So the difference is known as the attenuation crosstalk ratio, also known as ACR. The positive ACR calculations mean that the transmitter signal strength is stronger than that of the near end crosstalk. So ACR can be used to define a signal bandwidth, let's say 300 megahertz or 200 megahertz for category 6 cables, where signal to noise ratio are sufficient to support certain applications. So typically category 6 cables, 200 megahertz is where the signal noise ratio are sufficient to support the applications. It is interesting to note that the digital signal processing, also known as the DSP technology, can perform crosstalk cancellation, allowing some application to expand usable bandwidth up to and beyond the point of which calculated ACR equals 0. So certain equipment may be operating beyond that. Now, even so, minimum frequency for which the positive ACR is measured provides a benchmark to access the usable bandwidth of a twisted pair cable system. So at the end of the day, the maximum frequency for which the positive ACR is assured provides a benchmark. So what that means is basically, if the category 6 is 200 megahertz, that's the benchmark, that's what we go with, right? That's the standard, that's what the category 6 cable is made for. But the equipment which operates on that category 6 cable may be operating outside of that 200 megahertz rated for that ACR. So keep that in mind. So that's everything for that one. So next one is a PSF EXT loss. PSF EXT loss, which is basically Powersum find crosstalk. Again, you need to just know these things, right? I already have done this exams and classes, and I'm not a cabling specialist. I'm not a structured cabling guy. I'm a IT support and computer forensic guy. So basically, remember, if you don't understand this concept, at least read the definition and try to wrap your head around it. So the PSF EXT loss is a computation of the unwanted signal coupling from multiple transmitters at the near end into the neighboring pair measured at the find. So what causes this? Again, crosstalk, which is basically occurs when the signal from one wire capacitively or inductively couple into another wire, creating an interference. This is basically the primary cause. So if you want to know the primary cause, if your exam question asks what is the primary cause of PSF EXT loss, you need to know it is crosstalk. Crosstalk is the primary cause of PSF EXT loss. So the crosstalk occurs when the signal from one wire capacitively or inductively couple into another wire, creating interference. This is basically what it is, what this particular loss is. But this could also be caused by improper termination, which is the improper termination such as too much untwisting. Nick conductors can also introduce impedance mismatches, increasing the amount of crosstalk, just like previous losses that we discussed before. Defective termination hardware also can cause issues. Faulty termination hardware like bad keystone jacks or patch panels can also contribute to increased PSF EXT. Improper cable installation, poor cable installation practices such as improper cable routing or bounding or bending or bounding, or all of those things can cause PSF EXT loss. High operating frequencies. So remember, every cable has a rated frequency, but if you're operating at a very high frequency, even outside of that range, especially as operating frequencies increases, especially for example 10 base T, the effects of crosstalk become more pronounced and making PSF loss a more significant concern. So another one is the lossy materials. So while it generally believed that the lossy materials can, it can also create attenuation for PSEXT loss. So what in generally, what you need to understand for your exams when you are studying for structured cabling is that you know what these different losses are and their definitions. And if you can wrap your head around the technical concepts behind it, that's even better. So that's what you need to remember for this. Okay. So the next one we're going to look at is the PSACRF or PSELFEXT loss. Again, just remember what they are. So Powersum attenuation to crosstalk ratio find, or Powersum equal level far and crosstalk. It's a computation of the unwanted signal coupling from multiple transmitted at the near end into the neighboring pair measured at the far end relative to the received signal level measured at that same pair. So that's pretty much the definition of it. And this one also has the similar background for what causes it as the previous slide. The next one we're going to look at is the propagation delay. This is probably the easiest one to remember, which is basically, as it says, propagation delay in English. If you take two words, propagation and delay, and you look at the definition of those two words, it's basically the time needed for the transmission of a signal to travel the length of that's length of a single pair. So that's what the propagation delay, basically definition of it. Propagation delay is the amount, in other words, of time that passes between when a signal is transmitted and when that signal is received at the opposite end of that cable channel. So that's what basically the propagation delay. Another way to look at it, the effect is like a delay in time between when, let's think about like a lightning strike and the thunder head, except that in electrical signal it travels much faster than sound, right? If the propagation delay is like a lightning strike and you're hearing that lightning. So think about that way. Then we have the propagation delay skew, which is related to the previous slide, which is the propagation delay. Propagation delay skew is basically the difference between the propagation delay of any two pairs within the same cable stretch, right? Sorry, same cable sheath. So the delay skew is caused primarily because twisted pair cable is designed to have different twisted pair per foot, right, lay lengths. So delay skew could cause data transmitted over one wire pair to arrive out of sync with the data over another wire pair even in the same cable. So that's what the propagation delay skew is. And again, you need to understand what they are for your exams so that you can at least get a good grade, right? So the next one we're going to look at is the ANEXT loss, also known as the alien near end crosstalk, which is a measure of signal coupling from a near end disturbing pair into the disturbed pair of a neighboring cable or connector pair or part thereof measure at the near end. So that's what the definition for this particular loss. Again, just remember these definitions. These are very important for your exams. PSA next loss, which is basically the Powersum alien near end crosstalk. Again, the definition is a computation of signal coupling from multiple near end disturbing pairs into a disturbed pair of a neighboring channel, cable or connector pair or part thereof measured at the near end. Again, all of these things have the similar characteristic as what we have discussed in the previous slides. So that's why I'm not going into any more details other than the definition itself. Basically, these are all losses, right? So FEXT loss, also known as the alien far end crosstalk. The definition is a measure of signal coupling from a near end disturbing pair into a disturbed pair of a neighboring cable or connector pair or part thereof measured at the far end. Just at least remember the definition for your exams. PSA-FEXT loss, again Powersum alien far end crosstalk, which is basically a computation of signal coupling from multiple near end disturbing channel pairs into a disturbed pair of a neighboring channel or part thereof measured at the far end of the the cable, right? So basically, again, I'm going a little bit faster on the last few slides because the definitions are more important when you're starting out in structured cabling. So that's why I'm not going into detail. This to keep this lecture as short as possible, I'm going to go through them quickly, and maybe in the future lectures I will go in depth. Okay, so in this one, if I give you a little bit of background, basically unwanted signal coupling from one component or channel or permanent link to another is defined as alien crosstalk. So that's what basically the alien crosstalk is. So since the alien crosstalk is an indicator of differential or what we call the balanced signal coupling, the alien crosstalk cannot be adversely impacted by common mode noise, then we can go to depth of how alien crosstalk works and how it interact with things. But for today, what you need to understand is these definitions. PSA ACRF or PSA FEXT basically is a Powersum alien attenuation crosstalk ratio find, or the other one is a Powersum alien equal level find crosstalk. It's a computation of signal coupling from multiple pairs of disturbing channels to disturbed pair in another channel measured at the far end and relative to the received signal level in the disturbed pair at the far end. So again, at least remember these definitions. I will go over in depth some of these concepts in the future, but for now, to keep this lecture short, because it's already 28 minutes past since I started this video, so I'm just going to try to run it through now, but at least what we need to know for today for your exams is at least you remember the definitions that I went over, because it's part of the international standards that you need to know for your exams and excel in your academics. So that's everything today. If you want to check out my other information that I have already posted, please make sure that you check the description, and there is a link to the playlist for this lecture series. Please make sure to thumbs up this video and subscribe.